in my next set of notes and next set of lectures, I am going to talk about Laplace transform and how to evaluate Laplace transforms. So, moving ahead, so let me just start with the basic definition of Laplace transform. So, since we do not know the definition a priori, I am going to start the definition of Laplace transform by considering the Fourier integral formula. So, I am going to derive my Laplace transform by the Fourier integral formula. Okay. So, consider the Fourier integral formula of this function f1 of x. So, this is given by 1 by 2 pi integral from minus infinity to infinity e to the power I k x dk integral from minus infinity to infinity e to the power negative I k x I k t f 1 of t dt. So, that is my Fourier integral formula. Now, let us substitute. So, let us look at a particular situation where I substitute f 1 of x to be equal to, let us say, e to the power negative c x f of x h x, where h x is my regular Heaviside function. Okay. So, when I do that, I substitute here and I substitute here, I get the following expression. I get e to the power negative c x f of x equals, well, so, well, I can always write this function f 1 in terms of Heaviside function. This is for all x, or this is also equal to from this simple expression e to the power negative c x f x for x non negative. Well, if I do not want to use this Heaviside function expression. So, then I substitute this function, substitute, let us say this is my expression 1. So, substitute in 1, I get the following expression e to the power negative c x f x is equal to 1 by 2 pi integral from negative infinity to infinity. I have this e to the power I k x, notice this here, e to the power I k x d k. Then since I am using, so this function f 1 of x is such that there is a Heaviside function, or this is evaluated for all x positive. So, this second integral will change from negative infinity to infinity to 0 to infinity because of this Heaviside function. So, I have 0 to infinity e to the power minus t, and then I have I k plus c f of t dt. Okay. So, further I see that I have that f of x is e to the power c x by 2 pi. I have taken this function on the other side, integral from negative infinity to infinity e to the power I k x d k, the second integral 0 to infinity e to the power negative t I k plus c d f f t dt. So, now let us define my variable s to be I k plus c. So, in general this is a complex variable, right. So, if that is the case, then I have that d k is equal to d s by I. So, I am going to substitute all these expressions in this particular expression for f of x. So, I get the following new expression. I get f of x equals e to the power c x by 2 pi I integral. Now, notice that in the new variable, in the old variable k was from negative infinity to infinity, in the new variable my s is from c minus I times infinity to c plus I times infinity. Now, students should not confuse with this fact that how is this possible that we are adding a finite number to an infinite number. Well, notice that c is a real constant. So, I am going to talk about this sort of an integration where the real constant is finite while the imaginary value goes to infinity. So, this sort of an integral will be dealt slightly later in another lecture. So, then continuing to substitute, I get e to the power s minus x s minus s times x ds times integral 0 to infinity e to the power minus s t f of t dt. Now, I can absorb this e to the power c x inside and I get the following expression. So, 1 by 2 pi I integral c minus I times infinity to c plus I times infinity e to the power s x ds times integral 0 to infinity e to the power negative s t f t dt. Now, notice that I am going to define my Laplace transform of f, let us say Laplace transform. So, the Laplace transform is denoted by this integral. Okay. So, in particular the Laplace transform of f, also denoted by this curly L of f, is given by this integral 0 to infinity e to the power negative s t f of t dt. Similarly, the inverse transform, the inverse Laplace transform also denoted by L inverse of f is denoted by this integral given above, which is 1 by 2 pi I integral c minus I times infinity to c plus I times infinity times e to the power s t times the Laplace transform of f, which is denoted by f bar ds. So, I am going to denote this Laplace transform also by f bar s. So, that is this f bar s. So, now again briefly, this integral limits are not infinite as such, and I am going to talk about this inverse transform in another lecture. So, for the time being I am going to focus on Laplace transform of functions. So, I have introduced the Laplace transform and the definition of Laplace transform in this expression here. So, let us continue describing and looking at some common Laplace transform of some common functions here. Okay. So, to begin with, here are some simple examples. Laplace transform of 1 is nothing but integral e to the power negative s t times 1 dt from 0 to infinity, and when I do integration I get this is equal to 1 by s. Or if I have another example is, so these are some simple examples. Laplace transform of e to the power a t, this will be integral from 0 to infinity e to the power a t e to the power negative s t dt, which is also integral from 0 to infinity e to the power negative s, well negative t s minus a dt. So, this is nothing but the Laplace transform of, well, so this is the Laplace transform of 1 with variable s replaced by s minus a. So, I get the answer to be 1 by s minus a from above. So, then few more examples we can continue like this. We have the Laplace transform of, let us say, the sine function. So, sine a t. So, I can always introduce, instead of sine, I can always use the fact that my sine function is in terms of the exponential functions. So, the Euler's formula. So, this is e to the power I a t minus e to the power negative I a t divided by 2 I dt. So, then I get that this is equal to 1 by 2 I integral of the following expressions e to the power minus t s minus I a minus e to the power minus t s plus I a times dt. So, this can again be integrated very quickly and I get this is equal to 1 by 2 I times 1 by s minus I a minus 1 by s plus I a, and this can be simplified further and we get the expression that the Laplace transform of sine of a t is a by s square plus a square. Similarly, the Laplace transform of the cosine function is given by s divided by s square plus a square. And then in continuing in the same fashion, I have that the Laplace transform of this expression, this function sinh, or this is the hyperbolic sine, which is also the Laplace transform of e to the power a t minus e to the power minus a t by 2 is given to be a divided by s square minus a square. Then I have few more examples. The Laplace transform of, let us say, cos hyperbolic a t, which is also the Laplace transform of this exponential combination of exponential function e to the power a t plus e to the power minus a t by 2. This is equal to, we can evaluate this expression, this is given by s by s square minus a square. And then there is one more case, the Laplace transform of t to the power n is given by n factorial s to the power n plus 1. So, we can see that, so to find this, let us see quickly. I know that the Laplace transform of t to the power 0, which is the Laplace transform of 1, is 1 by s. So, similarly, Laplace transform of t to the power 1 is given by integral from 0 to t e to the power minus s t dt, and after integration by parts I am going to get 1 by s square. So, moving in the same fashion, I can see that I will get that the Laplace transform of t to the power n is, well, this will be 2 times s square. So, I get say 1 times 2 times 3 and so on n divided by s to the power n plus 1, or this is n factorial by s to the power n plus 1. Okay. Well, there are few more. Let us continue doing few more examples. Laplace transform of t to the power a, where a could be any real number this time, right. So, well, I need a to be positive as well, but a this time is a real number, is given by this integral 0 to infinity t to the power a e to the power minus s t dt. So, if I put x equals s t, if I use this variable x equals s t, I get that my Laplace transform changes to the following expression. So, I use that this is from 0 to infinity, then I have x to the power a divided by s to the power a times e to the power minus x, and then I have a dx. And then I can see that this integral reduces to gamma of a plus 1 divided by s of a plus 1, where I have assumed that s is positive as well. So, now what is gamma of the gamma function of any number a is given by this integral. So, where gamma function is given by this integral x to the power a minus 1 e to the power minus x dx. So, that is my gamma function. Notice that if a is an integer, then I get my previous expression for an integer value of a. Okay. So, continuing, let us look at slightly more complicated situation where we have to calculate the Laplace transform of a function which is not very trivial. So, let me introduce the function known as the error function. So, what is error function? So, let me call it as denoted by ERF of x. So, ERF of x is given by 2 by square root pi integral 0 to x e to the power minus s square ds. Okay. So, now I have to show that Laplace transform of the error function ERF of this argument a by 2 square root t equals 1 by s 1 minus e to the power negative a square root s. Okay. So, then what I see, so let us look at how to calculate this. So, my Laplace transform, let us say that this is my function f. So, my Laplace transform of f is given by integral 0 to infinity e to the power minus s t, then the second integral 0 to a by 2 square root t 2 by square root pi, and then we have minus let us say x square dx. Okay. And then I also have a dt here as well. Okay. So, then this integral will be equal to, so I am going to substitute x equals a by 2 square root t, or I have t given by a by 4 x square. Okay. So, let us substitute the following, and I am going to interchange the integral order. As well. Okay. So, then when we do that, I get my Laplace transform of f equals square 2 by square root pi times integral 0 to infinity e to the power, notice that my this factor is the same minus x square dx, but the other one is from 0 to, so this is a by 4, well, so in this case t is a square by 4 x square. So, my factor becomes a square by 4 x square, and inside the integrand is e to the power negative s t dt. Okay. So, the integrand remains the same, it is just that this the limit of this integral is changing. So, then what I have is that this integral is a simple exponential integral to be evaluated for an exponential function. So, that can be done immediately. So, this is 2 by square root pi integral 0 to infinity e to the power negative x square, and then my integral value times dx. So, the integral value, when we integrate, I get this equal to 1 by s times 1 minus e to the power negative a square s by 4 x square. Okay. So, then notice that this is now a single integral with respect to x. So, this will be 2 by square root pi, and I take this s common, out, and I get this two integrals. The two integrals are negative e to the power negative x square dx minus integral 0 to infinity e to the power negative x square plus a square s by 4 x square dx. So, this one I can immediately find that the value of this is square root pi by 2, and I have to evaluate this other integral. Let us call this other integral as I 2. So, that is what I want to evaluate. So, I have the expression for I 2 as follows. So, this is I 2 is 0 to infinity e to the power negative x square plus a square s by 4 x square dx. Now, notice, well, I am going to use some expressions, some simplifications for this I 2. It can be found that this I 2 is equal to this following integral given by this expression. This is equal to half of integral 0 to infinity 1 minus alpha by x square e to the power negative x plus alpha by x whole square plus 2 alpha times dx plus the second integral 0 to infinity 1 plus alpha by x square e to the power minus x plus alpha x, this time it will be x minus alpha by x square negative 2 alpha dx. Okay. Now, notice the reason for breaking this integral into two parts is, notice that first we are trying to complete the squares here. So, we are absorbing this x square and trying to write it in the form of whole square, and then notice that the second this integral is nothing but if we add it up, the second term vanishes in these expressions outside the exponential, and then when we take a half, we come back to this same integral as earlier. Now, here in this case alpha is given to be, we see that alpha is a by 2 square root s. Okay. Okay. So, then if I let my y to be x plus alpha by x in the first integral, and x minus alpha by x in this second integral, I am going to get my dy is 1 minus alpha by x square in the first case and 1 plus alpha by x square in the second case. So, then I see that with this sort of a change of variable, I get that my I 2 is, after simplification, I get this is equal to half e to the power minus 2 alpha times integral from negative infinity to infinity e to the power negative y square dy, and this can be easily evaluated and this is equal to square root pi by 2 e to the power negative 2 alpha. So, finally, my Laplace transform is, if we recall, this will be equal to 2 by s square root pi times square root pi by 2 minus I 2, right, and that will be equal to 1 by s times 1 minus e to the power minus 2 alpha, which is equal to 1 by s times 1 minus e to the power minus a square root s, and that is our answer that we were searching. Okay. So, this example was particularly taken because we wanted to show how to use Laplace transform, specifically how to use the different types of integrals, and typically you will see that in evaluating these Fourier transforms or Laplace transforms, you have to resort to integration techniques, let us say integration by parts, partial fractions, and using some well known integrals. So, it is necessary that most basic knowledge of calculus is known to the students, especially how to integrate certain functions. So, moving on, then let me just show another example. So, if my function f of t is given by this j 0 of a t. So, what is j 0? J 0 is the so called Bessel's function, of 0th order. So, Bessel's function of 0th order. Okay, so, this is, so I have to find what is my Laplace transform of the Bessel's function. So, this is something I have to find. So, again students are requested to look at the handbook of mathematical functions, that is what I have listed in my handout in my course description page. So, this is by Abramowitz and Stegen. So, please refer to this book to see the exact expression for this Bessel's function of order 0. Now, I will show you the expression for the Bessel's function in the series form. So, to begin with, my Laplace transform of this Bessel's function is the following expression. This is the Laplace transform of 1 minus a t whole square by 2 plus a t to the power 4 by 2 square 4 square minus a t to the power 6 plus 2 square divided by 2 square 4 square 6 square plus and so on. Now, which means that if I were to evaluate the Laplace transform, I can evaluate it term by term. So, I am going to get Laplace transform of 1 minus a square by 2 Laplace transform of t square plus a 4 by 2 square times 4 square Laplace transform of t 4 and minus so on. I get that this is equal to 1 by s minus 1 by 2 a square by s cube. I am just using the expression for the Laplace transform of t to the power n plus 1 times 3, I get 4 factorial on the numerator divided by 2 times 4 a to the power 4 by s to the power 5 minus and so on. And then when I take 1 by s common out, I get that this is equal to 1 minus 1 by 2 a by s square plus 1 times 3 by 2 times 4 a by s to the power 4 minus and so on. Notice that this is nothing but the binomial expansion of a plus s to the power half. A plus s, well, it is a square. So, this will be a plus s square. So, if I use a binomial expansion of this factor, I am going to get this series solution, this series expression above this. So, again simplifying further, this is equal to 1 by s times s square, well, I have a minus half sitting here. So, I get s square plus a square by s square to the power minus half, and after further simplification I get that this is equal to 1 by square root s square plus a square. So, that is my Laplace transform of the Bessel's function of the 0th order.